So welcome everybody to our last seminar for this session this year. And our speaker today is Tsuneya Yoshida. He will talk about exceptional points under symmetry and correlations. So welcome Tsuneya, and whenever you're ready, go ahead.
Thank you for the introduction. First of all, I would like to thank all of the organizers for inviting me this wonderful seminar series. I am Tsuneya Yoshida from University of Tsukuba. And today I am going to talk about exceptional points under symmetry and correlations. And here are my collaborators. So Professor Norio Kawakami and Robert Peters from Kyoto University, and Ryo Okugawa from Tohoku University, and Professor Yasuhiro Hatsugai from University of Tsukuba. And here is the outline of my talk. So basically, this talk is composed of 3 parts. In the first part, we discussed the symmetry protected exceptional link with local symmetry. In the second part, we introduced a discriminant indicator for exceptional. Oh, can you hear me? Is that okay? We introduced a discriminant indicator for system with inversion symmetry. And in the last part, we discussed a correlation effect on exceptional points, where we see that topological classification of point gap is reduced. The reduction occurs from G to G2. Okay, now let us, it's freezed. Just a moment, it's freezed. Now let us move on to the introduction. So recently, a variety of novel topological phenomena have been reported for non-Hermitian systems. A typical example is the emergence of exceptional points on which band touching occur for both of real and imaginary part, like this. And this band touching is protected by non-Hermitian topology. And a typical platform of the exceptional points are non-equilibrium systems, such as cold atoms and photonic systems. And here, as well as these dissipative systems, let me also note that correlated systems in equilibrium may show the exceptional point. To see this, let us focus on the single particle spectral weight described by the Green's function. And in this in this equation, we can see that the single particle spectral weight is governed by the non-Hermitian matrix. Here, let me note that the self-energy is non-Hermitian because its diagonal elements are complex. So in this way, exceptional points may emerge even in correlated systems in equilibrium. And here is a numerical analysis supporting the emergence of exceptional points in equilibrium systems. So firstly, let me show you the sketch of the spectral weight. Blue square illustrates the boundary of Brilliant zone. And in this figure, we can see 4 exceptional points denoted by green crosses. And these exceptional points are connected with Fermi arc. And numerical data supporting this sketch is shown here. So white dashed line corresponds to the boundary of the Brilliant zone. So this part corresponds to this part. And color denotes the spectral weight. And in this figure, we can see that the 2 exceptional points are connected by Fermi arc. So this data indicate that as well as dissipative systems, correlated equilibrium systems may show the exceptional point. Okay, now let us move on to part 1 of my talk. So motivation of this part is the following. In the above, we have seen the emergence of exceptional point in the absence of symmetry. However, in Hermitian cases, we know that symmetry enriches a topological structure. So it is natural to ask the interplay between symmetry and exceptional points. And our analysis focusing on the chiral symmetry discovered the symmetry protected exceptional links in 2-dimensional systems. And we can also apply our analysis to 3-dimensional system where we see the asymmetry protected exceptional surfaces. Okay, now let me explain the mechanism of symmetry protection. So to see this, let us analyze the 2x2 non-Hermitian Hamiltonian. And as a warm-up, let me start with a case without symmetry. Because our Hamiltonian is 2x2, it can be expanded with Pauli matrices and identity matrix like this, where B and D are real numbers, respectively. And diagonalizing this matrix, we can obtain the eigenvalues in this form. So here, we can see that the necessary condition for the exceptional points is written in these 2 equations. Because on the exceptional point, both of real and imaginary part shows the band touching, meaning that this part must be 0. And this condition is also the sufficient condition for the case of 2x2 matrix. I mean sufficient condition for the exceptional point for 2x2 matrix. Because suppose that, so here, suppose that these 2 conditions are satisfied, then with proper choice of basis, we can take vector B and D like this. So in this basis, we can rewrite the Hamiltonian like this up to the identity matrix. So we can see that Hamiltonian is not diagonalizable. So this is necessary and sufficient condition for the exceptional point for 2x2 Hamiltonian. So in the above, we have discussed the condition for the exceptional point. And here, let us consider two-dimensional system. In two-dimensional Brilliant zone, in order to have the exceptional points, we have to satisfy these two conditions simultaneously. Therefore, the exceptional points emerge as zero-dimensional objects. So here is a sketch illustrating this fact. Blue square denotes the boundary of Brilliant zone. And these two lines indicate the region where these two conditions are satisfied, respectively. So on the crossing point, the exceptional points emerge. So therefore, exceptional points from the zero-dimensional object. Now let us introduce a chiral symmetry. For system with chiral symmetry, the Hamiltonian satisfy this condition. In terms of vector B and this, this constraint is written like this. So here, let me remind you that the condition for the exceptional points are written in these two equations. So comparing these two sets of equations, we can see that the latter condition is automatically satisfied by symmetry because inner product of these two vectors are zero. So now let us again consider the two-dimensional Brilliant zone. In this case, satisfying this condition is enough to have the exceptional point. Therefore, exceptional point from the one-dimensional object. Again, let me show you the sketch illustrating this fact. Because this condition is automatically satisfied by symmetry, then arbitrary points are on this line. Exceptional points emerge, meaning that it formed a one-dimensional object. So let me stress that for the emergence of this exceptional link, symmetry plays an essential role. Actually, symmetry protects the this topological structure. Okay, now let me show you a correlated toy model showing the symmetry protected exceptional link. That is the honeycomb Hubbard model. And slight difference from the ordinary one is that the interaction U is spatially modulated. Here, specifically, let us suppose that interaction for A sublattice is stronger than that of B sublattice. Such a spatial modulation of interaction strengths is considered to be fabricated by optical Feshbach resonance. And another important point is that this many-body Hamiltonian, many-body Hermitian Hamiltonian preserve the chiral symmetry. And this many-body chiral symmetry results in this symmetry constraint at omega equal to 0, where effective Hamiltonian is the denominator of the Green's function. So this effective Hamiltonian describes the single particle spectral weight. This symmetry constraint is nothing but a chiral symmetry, which we have discussed in the second previous slides. So we may expect the emergence of symmetry protected exceptional links. And this is figure showing supporting the emergence of symmetry protected exceptional rings. In this figure, we plot the spectral weight at omega equal to 0 in correlated case. And color denotes the spectral weight. And white hexagon corresponds to the boundary of beryllium zone. And if the system is non-interacting, the Dirac cone appears at the corner of beryllium zone. And introducing the interaction, this Dirac cone splits into ring. Oh, yeah, like this. This is nothing but a symmetry protected exceptional ring. And here, let me note that the symmetry protected exceptional rings are accompanied by low energy excitation. Namely, inside of the ring, energy gap becomes pure imaginary, and then low energy excitation appears in this region. Okay, so let me briefly mention the case of a three-dimensional system. So in 3 dimensions, we can find the emergence of symmetry protected exceptional surfaces. So this can be understood as follows. So fixing the KZ, then the problem is reduced to the previous case, I mean 2-dimensional case, where we can see the symmetry protected exceptional surfaces. And this ring extends to Z direction, forming the surfaces. Okay, here is a summary of part 1 of my talk. In this part, we have discussed the symmetry protected exceptional ring with chiral symmetry, which is local, which is a kind of local symmetry. And here, let me briefly note that we can introduce the topological invariant characterizing the exceptional ring, that is a zero-Stern number. Okay, now let us move on to the second part of my talk. Firstly, let me briefly review the indicator of Hermitian cases. So symmetry indicator clarify whether a system must be topological without computation of topological invariant itself. An indicator is easily computed from data only at high symmetry point in the beryllium zone. So the symmetry indicator is an efficient tool to search the topological structure. So here, as an example, let us consider a one-dimensional insulator with chiral and inversion symmetry. And here, inversion symmetry is described by this equation. And our Hamiltonian is 2 by 2. And topological invariant characterizing the topological structure is shown here, that is a winding number. But without computing the integral, we can see that system, we can say that system is topological if the indicator takes a non-trivial value. Here, indicator is computed only from data at k equal to 0 and pi. So indicator plays an efficient filter of topological structure. Okay, so here is the motivation of this part. So the above symmetry indicator have been extended to non-Hermitian systems in these previous works. The key idea is that we can reduce the problem to the Hermitian case by introducing the doubled Hermitian Hamiltonian. Here, H is a non-Hermitian Hamiltonian, but putting it to the off-diagonal element, like this, we can obtain the Hermitian Hamiltonian. And introducing the indicator for Hermitian Hamiltonian, we can obtain the non-Hermitian, indicator for non-Hermitian systems. But such indicators do not serve as efficient filter of exceptional points because it includes the ambiguity arising from the reference energy. So in this part, I would like to introduce another type of indicator which serves as an efficient filter of exceptional points. Oh, there is a question. No?
Yes, there's the comment in the chat. Can you read it yourself?
Okay, what you call chiral symmetry is anti-Hermitian symmetry. Is this the case? All eigenvalue of the Hamiltonian in the unbroken phase. Sorry. In this case, all eigenvalue of the Hamiltonian are in the unbroken phase, both purely imaginary. Oh yeah, our Hamiltonian, maybe this is this one. This question is about this part. Am I right? If so, yeah. As this comment pointed out, our Hamiltonian is anti-Hermitian for many body anti-unitary for many body chiral symmetry. But symmetry is not broken for many body Hamiltonian. Okay. May I proceed?
Please.
Okay. So, okay. So here is the motivation of the second part. So I would like to introduce another type of indicator which does not include the ambiguity of reference energy. And here is the result of the second part. I mean, we have introduced a discriminant indicator which captures the exceptional point without ambiguity of reference energy. And for concreteness, we have introduced a discriminant indicator for system with inversion symmetry, which captures the exceptional point. And we can also introduce the indicator for symmetry protected exceptional surfaces for system with inversion and time reversal symmetry. Okay, so now let me go into the detail. So firstly, let me briefly review the definition of discriminant. So here is the definition. So consider a polynomial where a complex number. Then discriminant of this function is defined like this, where r's are roots of this polynomial. And here, let me note that the discriminant can be computed only from the coefficient alpha. Yeah, like this. This is the definition and the property of the discriminant indicator. And here in the following, let us consider a discriminant delta of this polynomial. Then this condition describes the emergence of exceptional points. Because if this condition is satisfied, at least two roots are equal each other, meaning that two bands touch. Okay. And we can also introduce a topological invariant defined with the discriminant delta. Here, the integral is taken along the closed loop. And if the winding number nu becomes non-zero, then inside of the loop, there is the vortex core where delta becomes 0. This fact means that if nu is finite, an exceptional point emerges. Okay. So now let me show you the discriminant indicator for exceptional points. Firstly, let us consider a system where the inversion symmetry is preserved. I mean, suppose that the Hamiltonian satisfies this condition. In terms of the discriminant, this constraint is rewritten like this. And this relation results in the relation between winding number nu and discriminant indicator. Here, the nu is computed along the closed loop illustrated here. Let me note that the information of this part is encoded to this part due to inversion symmetry. So focusing on this region is enough to search the exceptional one. And here, if discriminant indicator takes non-trivial value, then this relation indicates that the winding number must be odd, meaning that odd number of exceptional points emerge in this region. Okay, here let me analyze this 3x3 Hamiltonian to demonstrate that the above indicator works. And here is the phase diagram against gamma and m, which are parameter of this Hamiltonian. And in this figure, we can see that in the red color region, indicator takes non-trivial value, meaning that the exceptional points emerge in the red color region. For concreteness, let us focus on this parameter set represented with black dot. And here is the argument of delta for Brillouin zone. And this figure indicates that 5 exceptional points emerge in the right half of the Brillouin zone. And we can also confirm that on the vortex core, on the colored dots, the band touching occurs for both of real and imaginary parts. So this data demonstrate that the indicator successfully captures the exceptional points. Okay, let me finish this part by showing the derivation of this relation. So firstly, let me note that the integral along this path can be decomposed into two independent closed loops, this one and this one, because integral along this line and that line cancel each other due to periodicity of Brillouin zone. So nu can be rewritten like this. And as we see below, we can prove this relation for each binding number evaluated along these two lines. So combining this relation and this relation, we can obtain the relation between binding number and indicator. Okay, now let me prove this relation. So this relation can be proven by noticing the inversion symmetry. In the presence of inversion symmetry, this integral can be simplified into this form because integral along this line is equivalent to that of this line. And this integral can be evaluated like this, where n is integer, counting how many times delta crosses the branch cut. So from this relation, we can obtain this relation. So this is nothing but this relation, and therefore we obtain the relation between binding number and discriminant indicator. And here is a summary of second part of my talk. In this part, we have introduced a discriminant indicator which captures the exceptional points without ambiguity of reference energy. Okay, so now let us move on to the last part of my talk, where we see the reduction of topological classification of point gap. The motivation of this part is the following. So for Hermitian case, it is well known that a correlation effect changes the topological classification. So here, let us consider one-dimensional topological insulator of class A3, with chiral symmetry. Then such a system follows a Z classification at the non-interacting level. But in the presence of correlation, the classification changes into Z4. So this is a result of this is a result of Hermitian case. So here a question arises. Whether a similar reduction phenomenon occurs for no-Hermitian systems. And we have addressed this issue by focusing on the zero-dimensional no-Hermitian system with chiral symmetry. And our analysis elucidates that at a non-interacting level, the point gap topology is characterized by topological invariant taking integers. I mean, the system follows Z classification. However, in the presence of correlations, the classification result is reduced to Z2. Okay, before moving to no-Hermitian case, let me briefly review the Hermitian result. So in the above, we have seen the case of one-dimensional topological insulator with chiral symmetry. And in that case, a system follows Z classification at a non-interacting level. But turning on the interaction, the classification result is reduced to G4. And this fact can be understood as follows. So firstly, suppose that, firstly, let us focus on the non-interacting case. And suppose that we have the topological insulator characterized by winding number 4. And changing the one body parameter, the topological insulator changes into trivial insulator via gap closing. This is a result at non-interacting level. And turning on the interaction, we can see that this gap closing point does not extend to this direction. Therefore, we can smoothly connect the insulator in this region to insulator to this region without closing the gap. So this fact indicates that in the presence of correlations, the topological insulator with binding number 4 and trivial insulator are identical, topologically identical. Therefore, we end up with the G4 classification. Okay, this is a case of Hermitian Hamiltonian. So now let us move on to no-Hermitian case. Firstly, let me remind you the definition of point gap. So point gap opens if there is no energy eigenvalue is on the reference energy. Here is a sketch of energy spectrum. Horizontal and vertical axes are real and imaginary part. An orange dot denotes the energy eigenvalues. And we put the reference energy to the origin of the complex plane. So this sketch illustrates the case where point gap opens. And this sketch illustrates the case where point gap is closed because we can find the energy eigenvalue on the origin of the complex plane. So now let us move on to our model. Firstly, let me consider a spinless fermion. And our zero-dimensional model is composed of two orbitals, A and B. And our one-body Hamiltonian is shown here. And alpha and beta are real numbers. And this Hamiltonian preserves the chiral symmetry. And in the presence of the chiral symmetry, we can introduce the zero-dimensional topological invariant taking an integer. So here is a phase diagram against alpha and beta. If beta equals to 0, the system is topologically trivial. And turning on beta, system changes into a trivial phase, a topological phase. And on the green line, the point gap closes, as shown here. In this figure, we plot the real and the imaginary part of energy eigenvalue along this line. So if beta equals to 0, imaginary part are finite and point gap opens. And turning on beta, imaginary part becomes smaller and smaller, and then it becomes 0 at this point. And further increasing beta, the imaginary part, real part becomes finite and point gap again opens. This is a property of one-body Hamiltonian of our model. So now let us introduce the correlated Hamiltonian, many-body Hamiltonian. In order to introduce the Hubbard interaction, here we consider a system of fermion with spin half. And we descale the energy scale, we change the energy scale for downspin state. And this term, this one, describes the intra-orbital repulsive interaction. An important thing is that this model again preserves the chiral symmetry, many-body chiral symmetry. And if U equal to 0, this constraint of many-body Hamiltonian reproduces the symmetry constraint on the one-body Hamiltonian. Okay, now let us analyze the many-body Hamiltonian. Here, we plot the spectral flow along this line of the parameter space. So here, let me show you the movie of the spectral flow. So if beta equal to 0, the energy eigenvalues are aligned on the imaginary axis. And turning on the beta, spectrum energy eigenvalues flows like this. An important thing is that at beta equal to 0.5, point gap closes like this. So now let us introduce the interaction. And in a similar way, let me show you the spectral flow along this line of phase diagram. And here again, let me show you a movie. At beta equal to 0, eigenvalues are distributed like this. And turning on beta, the eigenvalues flows like this. An important thing is that in this case, no gap closing occurs between beta equals 0 and 1. So no gap closing along this line. And performing a similar analysis, we can confirm that along this line of this parameter space, gap closing does not occur. So here, we plot the absolute value of energy along this line of this face up of this parameter space. Lambda parameterize this path. If gap closing occurs, absolute value should become 0. However, in this figure, we can see that energy absolute value of the energy eigenvalue are finite for entire region of this line. This result indicates that we can smoothly connect the insulator of this region and insulator of this region by bypassing the gap closing point. And at a non-interacting level, this region corresponds to the topological trivial insulator, and this region corresponds to the topological insulator with zeroth Chern number 2. Therefore, we can end up with the deduction of topological classification from G to G2. Okay, so the above reduction phenomena can also be understood as follows. So in the above, we have imposed the many-body chiral symmetry. And in the non-interacting level, the Hamiltonian is quadratic. So the spectrum is governed by the one-body Hamiltonian, satisfying this condition. In this case, we can introduce a G invariant. However, in the presence of correlations, this picture is no longer valid. This picture is no longer valid. And in the correlated case, the invariant we can introduce is the G2 invariant defined here. This fact supports the deduction phenomena from G to G2. So here is the summary of the third part of my talk. In the above, we have discussed the reduction of topological classification from G to G2 for the point gap topology. So that is all. Thank you for your attention.
Thank you very much for your talk. Any comments, questions? Uwe.
Yes, hello. First, thank you very much for the talk. I'm a little bit puzzled concerning the effective operator structure that you are considering. You have your Hamiltonians there. Are these effective matrix Hamiltonians? And if yes, what is the dimensional of the matrix structure, the underlying matrix structure? Additionally, you have, of course, this dependence on the momentum operators or this momenta decay and so on. And it would be interesting to see what's the dimensionality of these matrices, effective matrices. Are they just 2, 3, 4, or are they n-dimensional in general?
Are you talking about the first part of my talk?
Any part.
Any part.
The problem is everywhere the same. Afterwards I will come to my actual question. But first I would like to understand what's the dimensional of the effective Hamiltonian that you are considering here.
Oh yeah, the size of the Hamiltonian we consider is the 2 by 2 in the first part, but the analysis, the same result holds for arbitrary sides of the Hamiltonian.
No, not so fast. 2 by 2 is clear. The only thing that can emerge are square root bound points.
For this talk, we have focused on the 2 by 2 Hamiltonian. Yeah, that's right. But introducing the topological invariant, just a moment. Topological invariant like this. So actually, this is the result of 4 by 4 Hamiltonian.
Yeah,
we
okay,
can
so
see the exceptional limit at the boundary.
Yeah, okay. So these systems are algebraically solvable. So you are always...
No, it's not solvable.
Of course, a fourth order polynomial is analytically solvable, so there's no problem.
I see.
So you can just write down for this algebraic part, you can just write down your fourth order quartic polynomial. You're doing you are getting the discriminant and you are checking for the exceptional points. So actually, once one could turn from the other side to your solutions actually. Just get the general solution of the quartic polynomial, check where the exceptional points are sitting, and then just doing small circles around the exceptional points, and you will find everything you have here. Otherwise,
actually, analysis of the first part applies for arbitrary size of matrix.
Okay, but the point is, these things are remaining algebraically. It means you have polynomials. Once you have polynomials, all what you are doing is you are considering Riemann surfaces of a certain genus. This means you have bubbles and certain number of holes in it. So that means that all your problem, your topological classification is just nothing else than the classification of the homology groups of this Riemann surface. So you will have a one-to-one mapping. But what you are doing then, you are just considering the plane of these momenta. And what you are getting is you get a very certain projection through this whole homology group. So, and I'm a little bit skeptic that you will be able, for instance, you consider two exceptional points, quartic problem. You can associate with these points chirality up, chirality down with the 2 points when you're encircling them. But when you're doing a big circle around them, you are getting zero. Nothing will happen. Similar phenomena will also happen in your case. So you should be sure that you have, when you're encircling your things or you're choosing this integral, that you have one exceptional point in it, or you should be able to count the number of the exceptional points. Otherwise, you will get ambiguity there.
Yeah, but maybe you are talking about
not the underlying geometry and the homology. It's the cycles that you are doing these cycle integrals. They can be rewritten out as integrals on Riemann surfaces. And this is just nothing else than homology theory, group theory.
Yeah, you are right if the binding number vanishes, but we are focusing
in a general case. In a general case, what you're getting is just a cumulative winding number, what you're getting. But you have no control how many exceptional points you will have in there, how the circles will move around. And so it's a very rough indicator that you are deriving there. It's interesting. But it's...
As you pointed out, indicator sometimes overlook the exceptional point. This is a case where the exceptional, even number of exceptional points emerge in this region. In this case, indicator becomes zero.
Exactly, yes, that's the point. Or any even number of them, when they are in a certain way paired with each other, you will also arrive at zero.
This is right. Yeah, you are right. Yeah, that's true.
And I'm wondering how you are controlling this. I'm wondering how you are controlling these effects.
Yeah, this indicator cannot capture exceptional points for such cases. Because indicator counts indicator elucidate where the exceptional points with an even or odd number of exceptional points emerge in this odd. Can you see the cursor? In this region.
Yeah,
So
in the
there
special
are-
case, but how you are sure that you have only one or two of these exceptional points there? You had figures there, you have 5 exceptional points or a higher number.
Right.
And when you're doing numerics, how you can control it? I'm just curious. I would like to.
I think the confusion is, what does the indicator indicate? And I think
Exactly.
you both have different
indicator-
ideas about it.
Yeah, okay.
Okay. Indicator indicate whether odd number of exceptional points emerge in this region.
Okay.
That's
As
all.
this
That's
relation.
all over.
Okay,
So
thank
as
you.
you pointed out, this cannot capture the exceptional even number of exceptional points emerging in this region. That is right.
Yeah, okay, thank you. That's all. So it's a very rough indicator that you have there.
Yeah. That's rough indicator, but simply
It's precise.
simply-
Odd or even. That's very precise.
Yeah, okay. Okay, if this is sufficient, okay, thank you.
Thank you.
There's also a comment in the chat by Himadri. Himadri, you want to read it out yourself?
Yeah, hello.
Yeah, we hear you.
So I think you showed that you use the Green's function where you showed up the self energy, which has this non-hermiticity. Now I was wondering that did you try to look at the spectral functions, which is the imaginary part of the Green's function, or did I miss that?
Oh yeah. Last moment. Let me go back to the first part. So yeah, by changing the spectral, by changing the parameter like interaction strength or temperature, the size of link changes. So for infinitesimal interaction strengths, it looks like points. And further increasing the interaction strength, the size of link becomes larger and larger, and finally, the link merges to the another link. So
Okay,
did I answer your question?
Yeah.
Okay.
Yeah. Thank you. I think got some.
Any more questions, comments? No questions anymore. Then I suggest we thank Tsuneya again. Thank you very much.
Thank you very much.
Thank you.
Thanks, Tsuneya.
That's it for this year. We will have a break over Christmas and we continue in January. So everybody have a happy and Merry Christmas.